Hello everyone. In this video, we are going to continue our previous topic on the equations of motion for an N-link robotic arm using the Lagrangian method. If you remember from last time, we showed that the equation of motion for N-link robots will be of form D matrix D times Q double dot plus C of Q and Q dot times Q dot vector plus G of Q equals tau. So G and tau are vector, Q and Q double dot are vector 2, and C and D are matrices. C matrix has these coefficients we call Christoffel symbols of first kind. D matrix is what we call the inertia matrix, is positive definite matrix, symmetric, and the way that we form the components of D is by finding the Vi and J omega I, the components of the Jacobian matrix for the linear velocity and angular velocity of a link, where linear velocity is defined at the centroid, and R is the rotation matrix, I is the inertia matrix defined about axes that are passing through the centroid but parallel to the local frame I. And when we combine, we get the D matrix. We had the potential due to gravity. We assume that's the only source of potential energy. And so the partial derivatives of P with respect to our generalized coordinate Q are forming our vector G. So we showed this. We derived the equations of motion for the 2 degree of freedom planar arm in the joint space, which was, as I said, of this form. Now, the first topic we discuss in this video is the equations of motion in the joint space if there is some force, right, at the tip. We call it F of tip. If that's the case, we have to add one extra term to our equations, and that is basically J transpose F of tip on the left side. Or we can say we can add this J transpose F of tip on the right side but with a negative sign. So the total torque applied to the joints is going to be tau and then minus J transpose times F of tip, right? And then say this is equal to your D matrix times Q double dot plus C matrix times Q dot and then plus vector G. Okay, and you might say, well, what is this? Well, if you know the relation between the torque at the joints and the force at the end effector is a relation that we know, tau equals J transpose times F. And so if this F is the extra F on the end effector that basically is applied to the environment, and the reaction of that is applied from environment to your end effector, to your robot, then not all of the torque that you're applying from your motors is going to be used to accelerate the joints. A portion of it is going to be taken away to compensate for holding this force F of t in balance, or to cancel out the effect of F of tip. Because assume that the robot does not move at all. So Q dot, Q double dot, they're all 0. If that is the case, right, then basically how much torque do you need to apply to your joints? If you remember in the past, if the only thing we have to do is to apply torques to the joints to cancel the weights of the members, then all you need to apply to the joints is tau equal G, right? Just the terms due to gravity. If now, in addition, so let's say we go back to this case here, if in addition to canceling these mg's in a static condition, at this end effector, you also are applying some force to the environment, and the reaction of that is applied to you. So you're applying this force F of tip to the environment by the end effector, and as I said, the reaction of that is applied back from environment to your end effector, then you also need J transpose times this F of tip in addition to the torques that you needed to cancel the mg terms. So your total torque now is going to be what? It is going to be G plus this term. So you can take this term to the other side. So G plus that term, right, is going to be all that I need in static condition. Now, if in addition to canceling the weight and applying so much force by the end effector to the environment, you also need to accelerate the joints, then these two terms will also come into play. So you clearly see this total equation is what? These two for motions, right? For motions of joints, this is the torque that you need for that. This is for weights of links, and this is for reaction from environment on end effector. So your torque should be sum of all this together to make your desired motion, cancel the weight, and apply so much of force to the environment. Good. So that's why we have this extra term. Now, before I get into the next topic, which are equations of motion in the task space, I want to emphasize one important thing. So far, if you have seen, all we have considered was really the D matrix, and D matrix directly comes from what? Considering the kinetic energy of the links. And here we assume that the input to each motor is directly the torque. But in real life, you know, the motors, right, that are driving these links, like this example here, we have seen it that the motors have some extra effects. What are they? One of them is the gearbox that comes with the motor. So there is this factor R that we have not discussed in this formulation yet. And the other one that we will see soon is the effect of what? The effect of the voltage and the internal dynamics of your DC motor, where you actually apply voltage as the input, not a torque. Torque is the output from the motor. So the internal dynamics of the motor should also be added, and when you do that, and the gearbox and everything, it changes this D matrix that we have in our formulations, this inertia matrix, it changes it to another matrix, a modified version of this D matrix, which we call M matrix. Okay, so the D matrix becomes the M matrix, and so instead of being D times Q double dot, then this guy becomes what? M times Q double dot. That's all I'm saying is you're gonna see me changing from D to M in the future. That's because we have not considered the effect of the gearbox and the internal effects of the DC motors, especially gearbox is the dominant one. The other thing is the friction. We have not discussed the effect of the friction on the joints yet. If we do that, that friction term will be added to our C matrix. So in the future, you might see my C matrix change a little bit from simply the partial derivatives of D components with respect to the Q variables to get those Christoffel symbols, right? All you get right now are the Christoffel symbols, which really, if you look at them as we discussed, they are the terms due to centripetal acceleration and Coriolis acceleration. That's all we have right now. But later, this term will be added to it some friction terms. Okay, and this D will be like M. So if you want really to consider all dynamics, then you have to bring those in, and that's what we're going to do in the next video. But right now, if we just neglect the effect of those, which in reality you can't, we are just driving the initial set of equations, just we have this simpler version. Good. So I just remind you about that, but we're going to see more discussions in a separate video. Now, what if you want the equations of motion in the task space, right? Instead of everything being about the torques and the q's and q dots and double dots, what if you want to write the equations of motion about task space? And what do you mean by task space? It means instead of your variable of interest being q and q dot, what if your variable of interest is xi, the twist, which is v and omega, right? And what if the driving agent behind the motion of the system, you switch from looking at the tau to look at f. And here this capital F has two components. It is like a 6x1 vector. The top 3 part of it, the 3x1 part of it, is the forces acting on the end effector, and the bottom part of it, this M, is the 3x1 moments acting on the end effector. Okay, so let me add that for you here. So this 6x1 vector, driving vector here, which is applied to your end effector, it has a 3x1 component and another 3x1 component. This F is basically the resultant force on end effector, and that M is not mass here. You see it's a vector, it's in bold font. So this is like the resultant moment on end effector. And this 6x1 vector that has both forces and moments on the effector, there is a terminology to it. We call it the wrench. Okay, so the wrench applied to the end effector, it's a combination of forces and moments on the end effector. So we consider this capital F as our driving agent of the motion, and then the result of the motion, instead of focusing on the 6x1 vector of joint velocities, we focus on the 6x1 vector of what? Linear velocity and angular velocity of the frame attached to the end effector. And we know this vector xi, we call it what? The end effector twist. Okay, so instead of tau and q dot, we focus on xi and capital F. If we write our equations of motion in terms of these two, then we say we have written our equations in the what? In the task space. Right? Because xi and f are task space entities. They are related to the motion of end effector in the task space and the things, forces, moments applied to it, instead of what is applied to the joints. Now, how do we do that? So what we need to do in this governing equation that we derived in the joint space, we have to convert or substitute for the terms q dots, as I said, the q double dot term, and the tau, and we should replace them with xi and basically capital F. And here, for simplicity, we neglect this extra term of the end effector and just go with the simpler term. But even if that guy exists, all we need to do, as we'll see, is to add the f of tip to what we will get. Okay, so it's not really a huge modification. Okay, so what do we do? First, substituting tau is not a big deal. As you just saw, this tau here is going to be J transpose times that capital F, okay? So clearly replacing tau is not a big deal. What about Q dot and Q double dot? Well, we know the relation of xi, your twist, is equal to J times Q dot. So if your J is an invertible matrix and you have n joints, then from here, right, your Q dot is simply going to be J inverse times xi. And you might say, what if my robot does not have 6 joints? Then you have to use the pseudo inverse of J, right? If it doesn't have 6 joints, then use J what? Plus instead of J inverse. But that's how you can what? You can replace your Q dot. So this relation here is going to go here, and that will take care of your Q dot terms. The only thing remaining is the Q double dot. What you need to do is just to take a time derivative from any of these equations, right? So let's say from this equation, if you take a time derivative, what will you get? You will get that xi dot, correct, is going to be what? Here is a product, so it's going to be time derivative of j, which we might show with j dot. That's not the small letter j, that's time derivative of j, times q dot, and then plus j times q double dot. And then from here, clearly your q double dot is going to be your xi dot, right? And then you take this j dot q dot to the other side, and then multiply both sides by j inverse, right, to get your q double dot term. Just move it a little bit to this side, and as I said, multiplying by j inverse, or if it's not a square, by j pseudo inverse, will get you what? Your q double dot. And so now this relation is going to go here. So now with everything properly replaced, you can go down and get your final equation of motion in the task space, which you can see here. So these equations 1, 2, and 3 are what we discussed. If you replace, you are going to get this equation in the blue box. This is your ultimate equation of motion in the, use a different color maybe, maybe this green. This is the ultimate equation of motion in the task space. F, the wrench, is equal to J transpose inverse times D times J inverse xi dot minus J dot J inverse xi plus C of Q and J inverse xi times J inverse xi. These are those Q dot terms that you can see are replaced here, as well as here in the equation that we have here. You see here, there is a Q dot. So those relations that I found for Q dot, this one here, a copy of that should also be sent right here too. Okay, and once you do that, as I said, you are going to get this important equation in green, and you can write this in a little bit nicer format. You can write it as this equation here, where this lambda matrix of Q and this eta matrix of Q and xi are going to be described by these equations for you. So if you want, you can write your task space equation into a nicer format, right? Because if you remember, your joint space was like tau equals some matrix like D times Q double dot. So now it is also a matrix of Q, right? But instead of Q double dot, you have xi dot. Remember, xi dot is, it has units of acceleration because xi is already velocity. So xi dot is acceleration. So this corresponds to this relation that you had. Instead of tau, you have F. Instead of d Q of U, you have lambda of Q. Instead of acceleration Q double dot, you have acceleration xi dot. And then instead of the whole thing C of Q and Q dot times Q dot plus G, so that whole thing, which you could write it as some general function f of Q and Q dot if you wanted, instead of that whole function. Now instead of f you have this eta function, and instead of Q dot you have xi. Okay, but again, your lambda, cap lambda function of Q is J transpose inverse T of Q, J inverse, and your eta function is a little bit longer, as you can see here. And inside eta, you also have the lambda. So before you can calculate eta, you need the lambda. Involved in it is the lambda function. Okay, and there is this matrix J dot. Again, pay attention, this J dot here is the time derivative of the J matrix. So each and every one of the entries in the J matrix, you have to take a time derivative from them. Okay, and that is your J dot matrix, and this is the equation in the task space. If later, as I said, we replace D matrix with M matrix, the only thing that would change in this equation will be in your lambda. You see, your lambda is a function of D, so later it will be a function of M instead of D, where M has the effects of gearbox in it. Okay, so we are going to ultimately see this form of lambda in our task space equation. Now remember that deriving the equations of motion in joint space, it was not really an easy process, even for the 2 degree of freedom planar arm, which is like the simplest robot you can imagine almost. And we had to find JV, J omega, I matrices, we had to find D's, we had to find C's, G's, and everything. And if you remember, we did that last time, right, in a separate OneNote page, and these two were those governing equations in terms of the masses of the links, the length of the links, and everything, right? So these were those governing equations. We have the acceleration terms in them, the double dots, we had the centripetal terms, we had the Coriolis terms like this one. And now if you want to for this same robot, if you want to do the equations of motion in task space, even for this robot, they are not going to look so nice. So what you need is your J. If you remember, for this matrix, for this robot, we have derived J, right? So this is the J Jacobian for this robot. J dot means time derivative. You definitely have to use chain rule. So for example, when you take time derivative of S1, it's going to be C1 times Q1 dot, or theta 1 dot, as you want to call it, right? So you have J dot. Your C is gonna just be modified. Instead of Q dot, you're gonna have zeta in it. And if I want to do that same thing here, my lambda matrix, my cap lambda, which is J transpose inverse D times J inverse, is gonna be this huge of a thing that you can see here. Is going to be this big thing inside this bracket. So here I use MATLAB symbolic, and you see this 2 by 2 giant matrix with all of these numbers. Now here, if you focus on this area, when you say my equation of motion is like this, F equal lambda xi dot plus eta. Now I showed you the lambda, right? It is this big matrix. My F is going to be Fx and Fy, the two forces that are applied to the end effector. And you might say, well, my F was the resultant force and moment, so what happened to it? Well, in this case, the only degrees of freedom that you consider for your end effector are just X and Y motion. You do not consider any rotation here, independent rotation. So you are going to trim it, really. You're not going to have 6 by 1F, you're going to have a 2 by 1F, which only has the two components of the resultant force, Fx and Fy. There is no Z, there is no independent rotation, so the M you completely neglect. The same thing with J. Instead of being a 6 by 2, in this case we trimmed it down to a 2 by 2. So here we only focus on two degrees of freedom of the end effector x and y. So your range is simply going to be fx and fy. Your lambda, I told you. Your xi dot, also your xi is like vx and vy, and your xi dot is going to be like ax and ay, accelerations of the end effector along x and y. And your eta is going to be much bigger. Your eta, you have to replace everything in it. So if you want to expand it, if this is just lambda, this big of a thing that you can see here, that huge thing is lambda, just imagine how big is eta gonna be. So in my next video that I'm going to show you how to use MATLAB symbolic to get these matrices and everything, I'll try to use MATLAB symbolic and we're gonna plug in numbers for A1, A2, M1, and M2 to simplify some of these calculations. You're still going to see if I'm in the joint space, the matrices D, C, G are not, and vector G's, they're not going to be like super scary looking. But when you get to lambda, it's still quite big, and when you get to eta, it's extremely large. Okay, so in general, the equations of motion in task space, they have much more terms. They get a lot longer, a lot bigger. Calculations of them are not easy. And you might say, why? Well, the main reason is this J inverse. That's the major thing. The transpose of J is not a big deal, but the inverse is. Okay, because you're inverting J, and that brings more and more stuff to it, and you also have J dot, right? So you are bringing more and more terms and multiplying them together. So if you look here, I have a 2 by 2, another 2 by 2, another 2 by 2, and then a 2 by 1. There are tons and tons of terms here multiplied together. Okay, and then the same thing here too, multiplying 3 matrices. So don't look for nice looking equations in task space. They are typically scary looking. And I'll show you, as I said in my next video, using the MATLAB symbolic. But they are typically long, big matrices. Now, as I said, if you want to include that force applied to the end effector, that F of tip, that the end effector applies to the environment or vice versa, right? The reaction of that, all you need to add to this nice looking equation that we just derived, all you need to add to it is an extra F term. That's all you need to add. So like what? Like instead of F being lambda xi dot plus eta of Q and xi, you also need to add one extra term to it, and that is F of tip. That's all you need to do. If you add that F of tip, then that will include it and you're good to go. Okay, now if you have constraints on the motion, and these constraints are equality constraints. Let's say you have more than one, you have k equality constraints, and you can write these constraints as Pfaffian constraints, which is like a matrix A of Q times vector Q dot equals 0. If you can write it this way, most of the constraint that you see on most of the robots, you can write as a Pfaffian constraint. Then all you need to do to modify your equations of motion is you add an extra term to the cost function that you use to minimize. Remember, the cost function that we have to minimize when we do Lagrangian method or Euler-Lagrange equation is this integral of Lagrangian versus time. We call it the action integral. You add to it now the term that is supposed to be 0, summation of AIQ times QI dot. Here AI is the ith row of matrix I. So this summation is another way to write this matrix product. And that term is ideally 0 if you have the correct Q of t, the correct function. If not, then it might be non-zero and positive. And so here you are trying to find the correct Q by finding the minimum of that, which could be 0. and you add these two terms together by combining them using what we call Lagrangian multipliers, lambdas. These are unknowns that you will add to your unknown q's. In general, remember, if your robot has n joints, you have n qi's that you have to find, correct? And so now if you have k constraints, you have to have k of these lambdas. So if that is the case, then your total number of unknowns in this case is going to be n plus k. And if you don't know exactly what is the Lagrangian multiplier, you can watch either my previous videos on using these Lagrangian multiplier to get equations of motion, or you can go to my playlist optimization and look at constraint optimization using Lagrangian multipliers, and you'll find more about them. So in this case, as I said, we add k more lambdas. We already had n q's, so we're going to have n plus q unknowns now. And what happens to your equations? Well, your equations are going to be very similar to what you had. You still have d times q double dot plus c of q dot. There is one extra q dot that I have to add here. And plus g of q is equal to tau, so you still have this, right? But now what you need to do is to add the extra term due to the second term in your cost function, and that is plus a transpose times lambda vector equals tau. So this is the only term that you're adding. Here, this lambda vector is the vector of all of your unknown lambdas. Sorry for the typos. It seems like for some reason I have a few typos here. So this is lambda 1. And then, you see, that's what happened. I tried to change it to 1. It changed the whole thing to number 1. And that's the only term that you have to add. Okay? And now, how many equations will you get? Well, these equations are over q's, so definitely here you are going to have n equations. Okay? So these terms that you see here, these guys are going to be n equations. And you have n plus k unknowns. So definitely not enough to solve for all of your q's, unless you also go back and use your constraint equations, the Pfaffian constraint. But these equations that you have, these dollar equations that you have, they are written in terms of the accelerations, q double dots. Your constraints are written in terms of q dots. So what you need to do, so they are also written over q double dots. Actually, what you can see here is I have nqi dots as unknowns instead of q, right? If, let's say, the problem you are going to solve is the forward dynamics problem, your goal is to find the acceleration terms plus lambdas. Of course, we really don't care about lambdas. The lambdas are just auxiliary parameters, auxiliary unknowns you add so you can solve the equations, right? The goal is ideally not to find lambdas. The ideal goal is just to find the q double dots, but you have to most of the time find lambdas unless you eliminate them somehow, if you can eliminate them. So we need, as I said, k more equations, and since these terms, original constraints are in terms of q dot, what we do, we take time derivative here from them, and that makes my constraint equation into acceleration terms. So it's going to be a q double dot plus a dot q dot equals 0, and now these equations have in them the q double dots. So these guys will also get you what? An extra k equations. So now you're going to have n plus k equations. And you also have n plus k what? Unknowns. So now ideally you should be able to solve for what? for everything that you want, although most of the time all that you want is really the q double dots. You do not care about lambdas, but now you have enough equations. Okay, so if your equations are what, as I said, your constraints are written as Pfaffian constraint. If they are written as Pfaffian constraint, that makes life a lot easier, okay, to incorporate them into your governing equation. You just add one extra term, as I said here, and you also take time derivative of your constraint, and those will give you some further extra equations, right? So let's say, for example, here in the case of this robot that you have, can we have any Pfaffian constraint on the motions, right? So as I said, it has to be like a matrix A times the q dots, right? Something like that to be equal to 0. Like what? Like, for example, let's say I want, and it can be A of q, it doesn't need to be constant. So for example, if I want, let's add the end effector here. If I want this end effector to only move in a horizontal direction, so it is limited to move inside the horizontal guide like this, and I have to keep the motion of this end effector entirely within that guide. So the only thing that this end effector can have, right, v, is going to be like that. Now, does that mean this v that is horizontal, or let's say v of y of the end effector, which is 0, correct? So this is v of x, it can be anything, but vy of the end effector, this has to be 0, and by y I mean y0 with respect to the base frame. Does it mean any constraint on the q's? For sure. Why? Because if you remember, in the case of this robot, the y of the end effector, let me add that for you, y of the end effector in base, right, in frame 0, it is equal to what? It is equal to a1 times sine of q1 and then plus a2 times sine of q1 plus q2. Right? Now when we take time derivative of this, then v of the end effector in base, this is going written in base, this is going to be equal to what? It is going to be equal to a1 c1 q1 dot and then plus a2 c12 times q1 dot plus q2 dot. And if I want to organize it, it is going to be like a1 c1 plus a2 c12, the whole thing times q1 dot, and then plus a2 c12 times q2 dot, this whole thing equals 0, right? That vy component, that guy has to be 0. Okay, now can I write this as a Pfaffian constraint? For sure. I can write it as what? Some A matrix times vector q dot to be equal to 0. And then matrix are going to be these two coefficients, right? So it's going to be a1 c1 plus a2 c12 and then a2 c12. So this is your matrix A of q. Definitely it is A of q because you have q's in this sine, in these cosine terms, and this is your q dots. So here for you k is equal to 1. You only have one constraint, and that is your constraint. Okay, so that is your A matrix, that is your q vector, And now you can incorporate that, add that to your equations of motion here. So basically what you need to do is to go back to your equations. We had D, we had C, we had G, nothing is new. We had tau. All you need is to add a transpose of Q times lambda equal to tau. So basically if I go back to what I found last time, which are these equations, I also need to add a transpose times lambda to them. So let me go ahead and try to copy this whole thing for you. And then we continue on that. So let's bring it down here. So these are my equations. Let me do a little bit of cleanup on them. Oh, sorry. You have to be a little bit close to them to do the good job. Good. So now what I need to do, my A transpose in this case is going to be what? My A transpose is going to be the transpose of that row matrix. So it is going to be a column matrix, right? So it's the transpose of that. So A1, C1, A2, C1, 2. Then A2, C1, 2. This thing is multiplied by vector lambda. But lambda here, you only have one lambda because you have one constraint. So that whole thing, if I want to say this is multiplied by vector lambda, then since I only have one lambda, I can say this is just like times lambda, or lambda 1 you might call it, doesn't matter. So now each one of these terms, this one is going to be added to the first equation, this one is going to be added to what? To the second equation. So what you will have is going to be plus, and this is going to be A1 C1 plus A2 C1 2 times lambda equals tau 1. And then here it is going to be plus A2 C1 2, correct, times lambda equals tau 2. So that's how you should what? You should modify your two equations, and now definitely you have three unknowns this time. You have the double dot terms that are your unknowns, and you can see them in both equations, and you also have this lambda now, if assuming that you have your tau, so you're doing a forward dynamics problem. So I have two equations, three unknowns, so that's where you need to take your constraint equation, which is like this, correct? This equation here that you can see. And you have to bring in the time derivative of this equation, or this one, as your extra equation, right? So what you need to do is, let's see if my marker works. For some reason, it's not cooperating well. Time to change the stylus. So here, I have to take a time derivative from one of these, doesn't matter. And if I go with what I have, so it's gonna be what? As we saw it, it's gonna be like a q double dot plus a dot times q dot equals 0. So if I want to add that for you here, the equation, as I said, is like a times q double dot plus a dot times q dot is equal to 0. So what's going to be? Your a, if you remember that the components are here, these are the components of a, so I have to take time derivative of them, but not for the first one, for the second one. So if I just want to write them as the first one, it was like this. This is your a, you multiplied by the q double dot terms, and then plus a dot, and then times the q dot. So I have to take time derivative, so it's going to be negative a1 sine 1 q1 dot, negative a2 sine 1 2 times q1 dot plus q2 dot, then negative a2 sine 1 2 q1 dot plus q2 dot. So you have to expand this, and if you do, you're going to get a1 c1 plus a2 c1 2 times q1 double dot, and then plus a2 c1 2 q2 double dot, then negative a1 s1 q1 dot squared, negative a2 s1 2 times q1 dot squared plus q1 dot q2 dots. Now you see the centripetal and Coriolis term show themselves. Then minus a2 s1 2 q1 dot q2 dot, then plus q2 dot squared is equal to 0. And this whole thing here is going to be your equation number 3. Okay, so now you have equation 1, you have equation 2, you have equation 3, and equation 3, the unknowns in it are really the double dots. So now you have 3 equations, 1, 2, 3, and if you want, you can write it as a coefficient matrix times the unknown vector plus, and then equal to the right hand side. So you can write your 1, 2, and 3 into, as I said, a coefficient matrix times your unknown vector, which is like q1 double dot, q2 double dot, and lambda, and then set it equal to a right hand side. And what is this right hand side? This right hand side is going to be some arbitrary, not arbitrary, some general function h of really q1 and q2 and q1 dot and q2 dot. Right, and the coefficient matrix, if you look at it, if you look at the terms multiplied by the double dots, they are just functions of q's, and also here they are also again functions of q's. So if you want, you can write it as some other function, and let's see, something like w of q1 and q2. Okay, where this guy is like 3 by 3 matrix. This is a 3 by 1 unknown vector, and this is a 3 by 1 known vector. Of course, here you also have the taus, tau 1 and tau 2. And so if you start from some initial condition, means you have the q values, and the torques are given to you, so everything is known. This w is known, and then from here, this unknown vector that you have is going to be w inverse times h. And then all you need in that calculation are the first 2 components of the result. Do you care about lambda? You don't. Okay, so this is how you go about solving your inverse dynamics problem if there is a Pfaffian constraint involved. And now, just out of curiosity, you might say, what is lambda? let's say if I find lambda, what is lambda gonna really be? And the answer is, it is going to be your constraint force. Okay, if you have here your end effector to stay only along this horizontal guide, you know, because the motion of it is horizontal from this guide, there will be some force applied in this direction, right? Some F of constraint force. That will force your end effector not to leave the guide, right? When there is a contact, there is a normal force. And this is going to be your lambda if you calculate it. So if somebody says, what is the force applied by the guide on the end effector at each point, that's what you need to calculate, and that is your lambda. Okay, so hopefully this video was beneficial to you and you learned how to handle some extra scenario cases. The case with there is some extra force at the end effector that you are applying to the environment or the environment is applying to you. What's the equation in the task space, and what's going to be the equations for us if we have some constraints. And in my next video that I wrote some code for you, I'm going to show you how to use your MATLAB symbolic and get these matrices C, D, vector G, lambda, eta, and so on, okay? So that is going to be my next video, and hopefully you are going to watch that. Thank you so much. See you in the next video.